Welcome to this episode of Woodlands on the Web, since I can't be there with you today. This is AP Chemistry Discussion 3.7 through 3.10, which covers solutions and colligative properties. This is part of the intermolecular forces unit because being able to overcome the intra-particle forces within a solute and interact with the interparticle forces between molecules of solvent is what determines whether or not something can become a solution. So here you have several examples of units of concentration. Obviously, the most important one for our purposes is molarity, and we've used that a lot. But there are some others to be aware of in terms of working with things that you might see. It's very unlikely that you'll see molality, but I still wanted to show you guys what it is just in case you do see it. So instead of liters of solution, it's kilograms of the solvent that goes on the bottom. All right. It has been a long while since we've done the sodium chloride mixture, proving sodium chloride was a homogeneous mixture lab. Okay, remember you used this you did this by showing that you could physically separate it with evaporation. So that part shows that it was a mixture. And hopefully we talked about how using or finding different percentages of different amounts of the solution would have given you a great way to show that it was homogeneous. Okay, so constant percent composition or molarity by using different sample sizes is the best method, but having a constant value for the mixture itself proves that it's a homogeneous mixture, especially because it all looks the same. You can't easily pick out the different parts. Okay, so that was one of the first labs that we did, but it was an AP level lab. All right, referring to molarity, we're actually going to be doing the spectrophotometry lab tomorrow in class on Friday, or you might be doing it on Monday, depending on which one you choose to do first. But I do want to briefly introduce what you're going to be doing in that. Okay, so you're going to be creating a standard curve for different concentrations of cobalt-2 chloride hexahydrate. Okay, we just did the hydrate lab, so now we know what that .6H2O means. Okay, cobalt chloride, when it's hydrated, is that kind of pink color that you guys used in your solubility lab the other day. But when it's anhydrous, it's actually that brilliant cobalt blue color that you associate with the color cobalt. Okay, so in order to make your concentrations, you're going to be starting with a stock solution of 0.200 molar cobalt-2 chloride hexahydrate. And what I want you to be able to do is figure out how much solid you would need for that. So we haven't done this in a while since the first time we did solutions. So let's go ahead and review that very briefly. Okay, we know that this is my given because remember, since capital M stands for moles over liters, that's going to be a conversion factor. You're never going to start with your molarity. You're always going to use molarity to convert either 2 moles or 2 liters, depending on which thing you're starting with. Okay, so we have a given amount of the solution we're trying to make, and we know that if we have liters on the top, that's going to go on the bottom. And considering the fact that my question is how many grams of this do I need, so how many grams of solid do I need, then I know that my connection between those two, between volume and grams for a solution, is moles. So I'm going to use my molarity as my second conversion factor, and then I'm going to go from moles to grams using molar mass. Okay, notice here that I went ahead and converted my 100 milliliters to 0.1 liters. That's something that you guys want to get in the habit of doing anytime you're dealing with solutions, because it just makes you have to do a little bit less work. You don't have to show College Board that you can convert from milliliters to liters. As long as you have the appropriate number there, they're fine with that if it's an AP grader. Okay, our concentration was 0.200 per liter. And here you do need to be careful with your molar mass in that you do have to take into account that there are 6 water molecules. So you're going to use the molar mass of 1 cobalt, 2 chlorines, 12 hydrogens, and 6 oxygens to take care of everything that's in the solid that you're going to be starting with. So that's where I get 237.93 from. okay, and that's per mole. So just to check my units, everything goes away except grams. So that means in order to make this stock solution, which I'm actually going to give you guys, but this is what I did to make it, except I'm going to multiply by probably 10 and give you a whole liter for the class. This is how much of the actual solid I would need in order to make my solution in the first place, okay? You guys are going to be looking at creating a calibration curve. And so that's going to generally look like a linear graph, at least hopefully. Okay, we're going to have our absorbance on the y-axis, and we're going to have our concentration in molarity on the x-axis. Okay, the thing here is that you want to make sure that these are regular intervals, because you may not be using concentrations that are concentration 1, 2, 3, and 4. They may be decimals. Okay, so you want to make sure that your starting point, the 0.2, is actually going to be your highest, if I remember correctly. So 0.2 molar is going to be your highest, and then you want to show your other points on there. So what you'll end up with is you're going to create known solutions. We'll review how to dilute a solution in just a second. But you're going to create known solutions and read their absorbances. So you're going to end up with a few data points that allow you to come up with a line of best fit. Okay? In this lab, you're also going to be given an unknown concentration of the cobalt-2 chloride. And the way that you're going to be able to determine its molarity in this case is going to be by reading the absorbance and finding what absorbance that correlates to on your line of best fit. Okay, so that's going to be the goal of using your calibration curve. It gives you a standard curve of concentration versus absorbance that you can use to compare an unknown sample against. Okay, just as a quick reminder, ionic solutions are going to involve ions dissociating. Okay, unfortunately, we're going to have to skip over the colligative properties virtual lab. I actually had you guys do a version of that before. We were going to do a little bit more complicated math this time. It's okay that we're not going to be able to get there. I think we'll still get the gist of the idea. But the main thing I wanted you all to see here is that it's going to depend on not only the concentration of the solute in the solvent or in the solution, it's also going to depend on how that particular species is going to dissociate. Okay, so in the case of 4 grams of sodium chloride, okay, if we do some converting, we would find that our concentration is going to be, I'm just going to use a rough estimate of molar mass. Okay, so 58-ish grams of NaCl per mole is going to give me 0.7 moles per liter of solution. But keep in mind, this is saying we have 100 grams of water total. That's the total solution mass. So our solution is really 0.1 liters. Therefore, I'm sorry, this was 0.07. Therefore, my molarity would be roughly 0.7 molar. Okay? So that concentration is going to be the concentration for sodium ions in solution and chloride ions in solution because they are in a 1-to-1 proportion. Okay, so since this is how that dissociates, the overall solution concentration is going to correlate to 1 unit of each ion that makes up that solution, so that would dissociate. Okay, so that is a little bit different than what's going to happen down here for magnesium chloride. Okay, so let's start out by finding the molarity of our solution first. So we have 3.58 grams of MgCl2. Its molar mass is 95.2 grams per mole. And so that's going to give us 0.038 moles per 0.200 liters of solution. So that gives me a concentration overall for the solution of 0.19 molar MgCl2. Okay, so the reason we would want to do this in the first place is, let's say we were trying to compare these two solutions. Is 4 grams of sodium chloride going to have more of an effect, or is roughly 4 grams of MgCl2 going to have more of an effect, noting that we've also doubled the volume of the solution? Okay, so we want to put things into molarity so that we can kind of put them into a standard form, but we're also going to go as far as comparing these by ion species. Okay, knowing that we're going to have Mg plus 2, there are one of those per solution, then the concentration of those ions is the same as the concentration of the solution. But since chloride dissociates into 2 chloride ions, so if you're looking at the beaker, you've got your Mg2 plus, and we have 2 Cl minuses, then the chloride ion concentration is going to be twice as high. So it's going to be the overall concentration of the solution times 2, which is 0.38 molar. Okay? If we were comparing these two things, because we had half as much water in the sodium chloride example, that one is going to have a greater effect on the overall colligative properties. So that means that by adding that amount of salt to that amount of water, you would cause the freezing point to lower more than you would with the magnesium chloride water combination. Okay, same thing would go for your other colligative properties. Okay, keep in mind polyatomic ions stay intact, because if you have, for example, NaNO3, this association is your ionic bond, but these atoms are covalently bonded. So when you dissociate that into its particles, you have sodium ions, and then your nitrate ions stay together. So if you had a 0.2 molar concentration of sodium nitrate, you would have 0.2 molar sodium ions in solution and 0.2 molar nitrate ions in solution. Okay? For dilutions, this is just to remind you how to do a dilution, because you're going to have to do this with the 0.2 molar cobalt chloride solution I give you. So remember that our dilution formula is M1V1 equals, I'm not going to re-record, sorry, M2V2. So if I was using this set of examples, or this example here, keep in mind your bigger number is going to be your first number. So in this case, my M1 is 3.0 molar. I want to know how much of that I'm going to use in order to make 100 milliliters. You don't have to convert to liters here, of a 0.1 molar stock solution. Okay, when I solve for that, I get 3.33 repeating milliliters. So in order to actually do this, I would mix that much of the stock solution, the 0.3 molar, with 96.67 milliliters of H2O in order to make the solution that I want. I'm going to stop here because I don't want my videos to be more than 15 minutes. The second part of this is going to be really short because I'm almost done. Okay, so hang on one second and find the next video, and I'll see you back there.